Okay, so let us start from where we left off yesterday. So actually we were solving the third exercise and we were trying to show that this function is onto, surjective. So we made a statement like this: for every y in the range there exists an element x in the domain such that g of x is equal to 1. Now this is an implication. This is an if-then statement. We can write it like this: if y is in the empty set, then there exists an element x also in the empty set such that gx is equal to y. So these two statements are actually the same thing. They have just been written in slightly different form. And this again, you can see that this is an implication. How this actually can still be rephrased like this: y is an element in the empty set implies there exists an element x in the empty set such that gx is equal to y. So this last statement is nothing but this two, and all of them they mean the same thing. So in this implication you can see that the hypothesis, this is the hypothesis and this is the conclusion. So the hypothesis is false. So regardless of what the conclusion is, the implication is true. In fact, this is the case where we say that an implication is vacuously true. That means there is no situation where this hypothesis holds. That's why we cannot find a situation where the conclusion does not hold. So in that sense, this is vacuously true. Nonetheless, this is true. So that means this statement is true. And that precisely tells us that this empty function is surjective. So we can now say this: hence the empty function g is surjective. So what do we find from this? From the discussion that we had in the previous video also, we find this thing, that if we have an empty function whose range is x, then whatever the range is, this is always injective. Every empty function is injective irrespective of the range. and the empty function is surjective if and only if the range is itself the empty set. So that means the empty function is bijective if and only if the range is empty. So we can write that conclusion like this. So not the empty function, since we are dealing with many empty functions. Or we can write like this: the only bijective empty function is the one having the empty set as its range. And that's where the solution to the third exercise ends. Okay, now we see the fourth one. Okay, so what this one says, in this section we give some cancellation laws. Cancellation loss for composition. I don't really understand why it draws this section. Anyway, so let us see what the exercise asks. Let f be a function with domain x, range y. Just like that, f tilde is also a function with domain domain x and range y. G is a function whose domain is y, range is z, and G tilde is a function with domain y and range z. Let these be functions. Okay, so what is there? Show that if G composition F equals G composition F tilde and G is injective. The marker is not working properly. I think it's because of dust. Injective, then F is equal to F tilde. Okay, so we have four functions and it is given that these two compositions are equal, and additionally that the first function, the one on the left side, is injective. Then we can cancel this function from both sides of this equation and we can have something like this. So it is somewhat like say you want to cancel suppose x and y are real variables and you have an equation like this. You can cancel 2 from both sides using ordinary laws of algebra, algebra of real numbers. So just like that, this is also a cancellation law. But keep in mind that there is a condition, G has to be injective. and the next part asks about that condition itself, and it says, is the same statement true? Is the same statement true if G is not injective? So this is one cancellation law. Like that, there is one more, and that one is this. Show that if, so this will involve G and G tilde and F. G composition F is equal to, okay, let me refill this. Maybe because of the dry weather, this is drying up pretty quickly. So it is given that G composition F is equal to G tilde composition F, and F is surjective, then we can cancel F from both sides to conclude that G is equal to G tilde. And just like the previous one, here also the question asks, the exercise asks, what happens if F is not surjective? Is the same statement true if F is not surjective? Okay, so let us now see the solution. So first of all, we are given that these two are equal and G is injective. So first assume G composition F is equal to G composition F tilde and G is injective. Okay. Now we have to prove this. So to prove that two functions are equal according to definition 337 of equality of two functions, first of all, both the functions should have the same domain and same range. Now if you look at the domain and range of both these functions, the domains are equal x for both f and f tilde. The ranges are also equal. So that part is okay. Now we have to show that they produce the same output for the same input. That means if we choose any element from this capital X, then fx, if that element is x, fx should be equal to f tilde x. So that's what we want to show. So let x belonging to x be any element. Now we use this condition, what is given to us, and note one more thing, that what is the domain of this function G composition F? G composition F maps X into Z. Like that, G composition F tilde also maps X into Z, because the intermediate sets vanish, that thing we have already discussed. So that's why, since G composition F has capital X as its domain, we can, this one also has X as its domain, we can apply both of this on this element X, and they will produce the same output because they are actually the same function. Then, but we write it like this: G of Fx, which is equal to G composition F of X, this is equal to G composition F tilde of X, and this is equal to G of F tilde of X. Okay. Now we use this condition that G is injective. Since G is injective and these two things, this Fx and F tilde X, where are they? See, F maps X into Y and F tilde also maps X into Y. So, since X is in X, Fx and F tilde X are elements in Y, and G is a function from Y into Z. So we have got two elements, Fx and F tilde X in Y, and G has been applied on them, and the outputs are same. Now since G is injective, the input should also be the same. Otherwise, it will look like this. Suppose the inputs are not same, these two are different elements in Y, and G maps both of them onto this single element. Because these two are equal, right? Then G fails to be injective, and that's why these two should be the same. So that's what we'll write. Since Fx and F tilde X are elements in Y and G is injective, we have Fx equal to F tilde X, and that's what we wanted to show, to conclude that F is equal to F tilde, because X is any element in the set X, which is the domain of both of these functions. Hence, F is equal to F tilde. Okay. Now, so this part is over. We have shown this. Now we have been asked to ascertain whether the same statement is true, whether we can have the same cancellation law if G is not injective, and this turns out to not be true. To show this, we need an example. So we have an example here. I have one with me, and it goes like this. Next, so that part is over. So we will need everything, the sets X, Y, Z and the relevant functions, that is G, F and F tilde. So X, Y and Z, all of them are taken to be this set, and let F f tilde and g be defined as this. The value of f at 1 is defined to be the same as the value of f at 2, which is defined to be equal to 1, and the value of f at 3 is defined to be equal to 2 or 3. Okay, so we have defined f. Then what is f tilde? F tilde at 1 is defined to be equal to f tilde at 2, which is defined to be equal to 2, and f tilde at 3 is defined to be equal to 3, and g is defined to be equal to nothing but f. Okay, so g is basically the same thing as f. F and g are the same function. Okay, now what do we get from this particular example? We need to look at g composition f and g composition f tilde. So let's calculate these two functions. First we look at g composition f. We just need to see what this function does to the inputs. So first we calculate the value at 1. We first apply f on 1 according to the definition of composition. F of 1 is what? 1. On that one we apply g then. And since g is nothing but f, so once again we apply f on that 1, and thereby we get 1. F of 1 is 1, g of that one is nothing but f of 1, which is again 1. And what about g composition f tilde? F tilde of 1 is 2, and on that 2, I need to write this way. F tilde of 1 is 2. On that 2 we are applying g, and since g is f, so that means ultimately we have f2, and f2 is again 1. So these two things are equal. Okay. Then g composition f of 2, and this is equal to f of 2 is 1, and g of 1 means f of 1, which is again 1. So this is 1. G composition f tilde of 2. Okay, f tilde of 2 is 2, and g of 2 means f of 2, which is 1. So this is also equal to 1. So the functions g composition f and g composition f tilde agree at the points 1 and 2. So we only thing left is 3. So f of 3 is 3. G of 3 means again f of 3. So that is equal to 3. And what about this? F tilde of 3 is also 3. On that we are applying g, which is nothing but f. So f of 3 is 3. So this is also equal to this. Hence, G composition f is equal to G composition f tilde. For these particular functions, we are having this. But f is not equal to f tilde. Since f of 1 is not equal to f tilde of 1. F of 1 is 1, but f tilde of 1 is 2. So you see that in this case, we cannot cancel g from both sides of this equation to conclude that f is equal to f tilde, because they are not equal. And what has gone wrong? I mean, we have already proved cancellation law, but there we had the additional condition on G, that G is injective, which now is not true. You see, G is F, and F maps both 1 and 2 onto 1. So two different elements in the domain are getting mapped to onto the same element, and that is that says that G is not injective. Note that G is not injective. So that means the part of the exercise that asks what happens if G is not injective, we can say that the cancellation law is not necessarily true. So we can write that in fact. Hence, we don't have this implying if G is not injective. You may say that for some F and G, things may turn out to be actually true. I mean, this implication may actually be true even when G is not injective. Maybe, but keep in mind that when we write a statement like this implication, we say that the implication is true only when in all cases it is true. When we write something that involves not some particular function but some variable functions or something variable, then such a statement is said to be true without saying anything else, if that is true for all the values of the variable. So that's why we are writing that this is not we don't have this does not mean that all the time it fails. It may turn out to be true for some values of G and F even when G is not injective, but there are cases like this where it fails. Okay, it's not necessarily always true. Okay, so now we go to the second part of the solution. And in the second part, we have a similar cancellation law. Okay, so next, assume this: G composition F is equal to G tilde composition F, and F is surjective. So now F is constant, F is there on both sides of the equation, but G and G tilde are two functions which may or may not be equal. We have to show that they are equal. Okay. So just like what we did in the previous test, you look at the functions G and G tilde, both map Y onto Z. That means they both have Y as domain and Z as range. So the part of definition 337 of equality of functions, which says that two functions are equal if first of all they have the same domain and range, so that part is okay for us, for G and G tilde. Now we have to show that they agree at every point in Y. So we arbitrarily choose a point. Let point means element. Point, element, member, these words are being used synonymously. Let Y belonging to Y be any element. Okay, now we use the fact that F is surjective and F has domain X and range Y. So since Y is an element in the range of F, so there will be one point in the domain of F which F maps onto this point, because that's what surjectivity means. So that's why, since Y belongs to Y and F is surjective, there exists some element X belonging to X such that Y is equal to F of X. Okay, right. Now if we look at these two functions, G composition F and G tilde composition F, we can see that, okay, let me just write the domains and ranges once more. This is X, this is Y, and this is Z. So F maps X into Y. G maps Y into Z, G tilde also maps Y into Z. So that means G composition F maps X into Z. The intermediate set vanishes. Just like that, G tilde composition F also maps X into Z. And we now have an element X in the domain of these two functions. We have X here. So we can apply these two functions on X, and actually we will have the same output because these two functions are equal. So that's why now or we can write it like this: G of okay, let me argue like this. Now G of Y is equal to, since Y is equal to Fx, I can write G of Fx, which is nothing but G composition F of X, and this is equal to G tilde composition F of X, because these two functions are equal. So at X they will have the same value. This again is equal to G tilde of Fx by the definition of composition of mappings, and here we replace again Fx by Y. So what have we got here? You see, Y was any element in Y. At that arbitrary element, we have shown that G and G tilde agree, and these two functions have Y as their domain, common domain. Hence, G is equal to G tilde. So this cancellation law has also been proved. So now, just like the previous one, this one, we have to now deal with the case where F is not surjective. Then things can go wrong. So here also we have one example. Next, let X be this set consisting of the two numbers 1 and 2, and Y and Z be this set consisting of the three numbers 1, 2 and 3. We are not over yet. And let f, g and g tilde be defined like this. F of 1 is defined to be equal to f of 2, which is defined to be equal to 1. Note that for f this much is enough. Why? Because the domain of f is x, which has 2 points. So at these 2 points we have defined the value of f. So f has been defined. Now what about g? G, however, has domain y. So at these 3 points we have to define g, and such is the case with g tilde also. So g of 1 is defined to be equal to 1. G of 2 is 2. G of 3 is 3. And what about that other function? G tilde of 1 is defined to be equal to 1. In the other two, at the other 2 points we switch the values. Here we had 2, we write 3. Here we had 3, we write 2. Okay. Now let's see the situation for these choices. So, like the previous